All right. In our lecture 5 of Strength of Material 1, we want to look at analysis of composite sections. Good. In our lecture 5 of Strength of Material 1, we want to look at analysis of composite sections. Our lecture outline is composed of the introduction, analysis of composite section, and also some work examples as well. Good. Let's quickly or kindly look at the introduction. We say that a composite section consists of two or more materials bonded together or into brackets rigidly jointed, such that the straining action of the external load is shared by the material forming the section. A composite section consists of two or more materials bonded together such that the straining action of the external load is shared by the material forming the section. The end of the different material of the bar or section are held together under loading conditions. Okay, good. For composite sections, the total external load is shared by the material as they undergo deformation. Note, note, note that the materials may have the same length or different length as shown in figure 1. Okay, that is A and B. I'll show you soon in the next slide. Okay, so this is the ones that they are talking about. You can see that this is material 1 made of a different material, and also this is a material 2 made of a different material. Okay, you can see it over here. If it is a circular one too, you can see how it will show like, and you can see the material 1, you can see the material 2. Okay. An example is the concrete we used to cast at site. Okay, you realize that there is always a still in the middle, and then let me say we cast the concrete around it. So that one can also be called a composite section. Exactly. So I want you to draw your mind home again. That is why I said that you should note that the material may have the same length or different length as shown in the figure that I just showed you. Okay. So you can see over here it is made of the same length, but over here too they are made of different length. Okay. They are made of different length. So once this is a different material, this is also a different material, I should tell you that their modulus of elasticities are obviously going to be different. Okay. Good. Parameters of interest are stress. Parameters of interest are stress induced in each material. Okay. And these are the things that we are going to be calculating for. Okay. And also load carried by each member and the deformation. Okay. So these are some of the things we are going to be looking for. So just as I explained to you, just as I discussed to you over here. Okay. In case of a circular section, you may see in a plan form or in a plan view, this is how it can be displayed or seen like. But when you take the front elevation, maybe you'll be seeing something like this. Yes, you'll be seeing something like this. It will be the front elevation or what? Back elevation. Okay, so just don't get confused. Just don't get confused. So let's proceed. So this is a compound or compound bars. Okay, when we say something is a compound, two or more substance. You understand? So let's look at examples of composite sections. We are still under the introduction though. Let's look at some examples of composite sections. 1, we have the composite beam. Okay, a beam can be made up of, let me say, uh, a steel and concrete. So you can see that you can call it composite because it's two or more materials. Unlike in some cases, you realize that they are still alone. Let's look at 1. And our 1 says that composite beam, into brackets, a concrete slab cast on top of a steel, that is I-beam. Example, Kwame Nkrumah Circle Interchange. Okay, Obechebi, Lamte, and even Circle Interchange. You realize that these same composite beams idea were adopted over there to solve problems. Okay, that is a concrete slab okay, is cast on top of an I hot beam. All those beam are I beams you are seeing over there, okay, whereby a concrete slab is cast on top of it. As simple as that. So let's also look at the composite columns, okay, and it's just a steel column encased in concrete. The word is encased in concrete. Okay. And the third one we are going to look at over here is reinforced concrete section. Okay. It will be beam, column, slab, etc. Okay. That is reinforced concrete section. We have so many kind of sections whereby concrete and steel can be molded into. Okay. So we can't just limit it to just let me say beams and columns. Okay. That is why you see this over here, reinforced concrete section. That is, it is just relating it to general. Okay, we also have some arches like this. Okay, they are also made of, let me say, concrete and steel. So what about those two? So that is why you have to see the idea that reinforced concrete sections have to be introduced. Okay, good. Let's look at composite sections. Okay, that is composite bars or sections must justify the following two conditions. The first one we should always consider is the equilibrium condition. The equilibrium condition. And then the second one we are also supposed to know about is the compatibility condition. One may ask, what is equilibrium condition about? The equilibrium condition is the total external load on the composite bar. Okay, the total external load on the composite bar is equal to the sum of the load carried by each different material. That is what the equilibrium condition is about. It's saying that the total external load on the composite bar, okay, is equal to the sum of the load carried by each different member. Okay, as simple as that, as simple as that, as simple as that. I'll be showing you that very soon. Let's also look at the compatibility condition. And the compatibility condition is saying that the extension, okay, if I say extension, that is the change in length or compression in each bar is equal. Okay, because they are held together. Okay, hence deformation in length, that is strain in each bar, is always equal. Okay, so at the end of the day, let's say if you are using aluminum and then let me say copper, you realize that the change in length in copper is going to be equal to the change in length in what? Aluminum, and vice versa. Exactly. Exactly. So let's look at composite. Also, we are saying that composite sections must satisfy both equilibrium and compatibility condition. So you should take note. This is a very key point to be able to solve, uh, let me say, composite questions, okay, on a high accuracy. If you want to be precise, you have to adopt to these two things, okay? And that is, you should always make sure that your solution is correlated to the equilibrium condition and also the compatibility condition. Okay, exactly, 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 exactly. So let's quickly look at this side. But before that, if we want to talk about the equilibrium condition and then the compatibility condition mathematically, then it implies that, let's say, the equilibrium condition, it could just mathematically, it can be explained as this. Okay, that is the total load is just equal to the hot. Let's say if we are using steel and copper. Okay, let's say if you are using the materials, you are using a steel and copper. Steel is represented as S, okay, and then our copper in this case, we can denote it as C. Okay, so if you see PC, just know that load in hot copper. Okay, so the P S is a load in steel plus the hot load in hot copper. Okay, and this is what the equilibrium condition is talking about. For the compatibility condition, it means that the change in length, okay, in steel will always be equal to what? The change in length in the copper. Okay, so just these are mathematically, or what I have been saying theoretically. This is what I have explained, or this is how it has been explained mathematically. So at this point, I want to take some few questions before we proceed. And is anyone having any question to ask? Any challenges before we proceed? Any question, any contribution, any challenges? All right. All right. So let's proceed. So let's look at composite section. We are continuing. Okay. Yes. So in our continuation, we are also saying that in the problem we have, in the problem we have considered so far, we have used only the condition of static equilibrium and Hooke's law to find the deformation. In the case of composite section, the condition of static equilibrium are not enough to determine the forces in the members. Hence, one more other condition referred to as compatibility condition must be applied. Note, note that the compatibility condition relates to the deformation of the materials. The deformation of the two materials are equal. That is, let's say in the case of the strains in the two materials are equal. Okay. That is, let's say in this case, the strain in the two materials are equal. We are saying that you should take note that the compatibility condition relates to the deformation of the material. The compatibility condition relates to the what? Formation of the material. And the deformation of the two material are equal. Okay. In this case, the strain in the two materials are equal. As simple as that. So let's kindly have a look at this over here. You can see that this is a composite section in tension. Okay, you can see this going away from the bar. This is also going away from the bar, indicating that this is in tension, and this is material 1, this is material 2. Okay, so P is just the load. Let me say the total load. And also P1 can be used to denote the load carried by material 1. P2 can also be used to denote the load carried by material 2. The presence of A1 and A2 tells us we are always going to calculate for the what? The cross-sectional area of material 1, and also we are going to be calculating for the cross-sectional area of what? Material 2. Okay. Also, we must also know the stress in material 1. We must also know the stress in material 2. For the Young modulus, in most cases, they might be provided, or we may also be asked to what? Find for them. Okay. We must also be able to find for them. All what we are going to be solving now is just what I have summarized over here. Because at the end of the day, it is out of this thing that I've written over here. And we have already derived so formulas about this. Those are what we are going to be deducing to solve the work. So after teaching this page, smart students knew that I'm even done teaching whatever we are supposed to teach. At this point, we are even supposed to start solving questions. But let's just see how we can be able to finish going through the slide, and now we can continue solving some practical questions to see how we can build our understandings. Exactly. Exactly. So let's continue with the equilibrium condition. Okay. So for equilibrium condition, load carried by material 1 plus load carried by material 2 must be equal to the total load. Okay. So that is, we are saying that P1 plus P2 should always be equal to what? P. You can keep this equation somewhere, and you all know that stress is equal to what? Your stress is equal to what? Load over what? Area. So at the end of the day, if you make P the subject, what are you going to realize? You realize that if P is the subject, then you're going to get stress times what? Area. Okay. So at the end of the day, your formula to get your P, or the load, is equal to stress times, and that is what has been put over here. Okay, that is all what they are trying to explain in this line over here. Yes, yes, yes. Also, I want you to note that um I want you to note that P1 can be expressed as this, and also P2 can be expressed as this. Okay, in terms of this equation that I have written over here. Okay, in terms of this equation that I have written over here. Yes. So by substitution, you realize that from equation 1, we have now written it as this again. As simple as that. Let's also look at the compatibility condition. For the compatibility condition, we are saying that the deformation of material 1 must be equal to the deformation of material 2, and mathematically this is the meaning of that. Mathematically this is the meaning of that. Okay, mathematically this is the meaning of that. Okay, good. From lecture 1 we learned that strain is equal to change in length over original length. So if you want to make the change in length the subject, you realize that then our formula is now going to become our stress times the length. Okay. So that is what you are seeing over here. Our strain times the length, and that is what you are seeing over here. That is what you are seeing over here. Okay. So that is what you are seeing over here. And also, you have to know that this same strain that I have underlined over here, this same strain that I have underlined over here, from the same lecture 1, we learned that elasticity is equal to what? Stress over strain. So if you make strain the subject, what are you going to get? Your strain is now going to become, let me say, stress over elasticity. Okay. So if you do that substitution over here, then finally we can say that our change in length, okay, our change in length is going to be equal to, let me say, stress over the elasticity. Stress over elasticity times our length. You see? So finally, I can rewrite it over here. Therefore, we can say that our change in length is equal to our stress over elasticity times the length. Okay. So this that I have circled over here, you still see it over here, and that is what has been expressed in this case. Okay, that is what has been expressed in this case. Okay, so don't get confused. Don't get confused. Don't get confused. So this is what I have rewritten as this over here. Don't get confused. Okay. So at the end of the day, by substitution, you realize that our stress 1, or let me say our change in length in material 1 is equal to what change in length in material 2 can be written as this. Okay. It's just being able to play with the formulas and do the substitutions better. That is why I always advise that you will be able to do the change of subject. It is a major thing or problem that if you're able to break through, you are going to encounter a lot of success out of. Exactly. 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 Take note. Please take note that. Please take note. Take note. Take note. Take note that if the length of the composite section is equal, then L1 is equal to L2 is equal to L. Okay. And in that case, by substitution, this is the formula we are going to be using. Okay. That is if the lengths are equal, then it means that for the compatibility condition, our stress, our stress in material 1 over the elasticity in material 1 is going to be equal to the stress in material 2 over the elasticity in material 2. Okay. So you just have to solve equation 2 and equation 4, or equation 2 and equation 5 simultaneously to determine the stresses in each member. Okay. Let's quickly look at modular ratio. Modular ratio is the ratio of modulus of elasticity of two different materials. Modular ratio is the ratio of modulus of elasticity of two different materials. Note that modular ratio has no unit and may be given instead of the actual modulus of elasticity of the individual material. Where modular ratio is given, express the modulus of elasticity of the given material to match the ratio given. The modular ratio may be denoted by, let's say, N or M. Okay, so this is an example of modular ratio. That is the elasticity or the Young modulus in material 1 over the Young modulus of material 2. At the end of the day, you realize that they are all in Newton per millimeter squared. So at the end of the day, let's say Newton per millimeter squared will cancel out what Newton per millimeter squared. And that is why we are saying that they have no unit. Okay. So this will cancel this. That is why we say that they have no unit. Do you understand me? Uh-huh. So these are some key notes you should be able to note before we can be able to start solving some work examples. Let's quickly brush through them and see how best we can proceed. So please take note that for the equilibrium condition, still for the equilibrium condition, we are continuing to say that the load carried by each material must be equal to the total load. Okay. For example, if the composite section is made up of, to say, 3 materials, then at the end of the day, this is how our load can also be expressed. Okay. It's going to be P1 plus P2 plus P3 is equal to the what? Total P. And we are also continuing to say that the P1 is just the what? The load in material 1. The P2 is the load in material 2. And then the P3 is the load in material 3. Will all be equal to the what? The total load. That is in the case of equilibrium condition. Okay. That is in the case of equilibrium condition. Let me quickly denote it or highlight it with a good pen for you to see exactly. Exactly. And also for the compatibility condition, we are saying that for compatibility condition, the change in length of the materials must be equal. Okay. So at the end of the day, change in length in material 1 will be equal to the change in length in material 2, equal to the change in length in material 3. As simple as ABC. As simple as ABC. Let's take note of some of these key points. So these are some key notes I wish you'll be able to put down. These are some key notes I wish you can be able to write down. So let's continue. The main consideration is calculation of load and stresses in the composite section. Sometimes the change in length of the section are also required to be calculated. Note that in the computation, either the stress. Bismarck, please kindly clean what you have written on my screen. Note that in the computation, either the stress induced in the material or the load carried by each material may be calculated first. If the stresses induced in the material are calculated first, the load carried by each member can be calculated using the relation. Okay, so you can see it is being expressed as this, and then the I you are seeing over there is, it means to infinity. Don't get confused. And similarly, if the load carried by each member is first calculated, the stress induced in each member can be calculated using the relation. This is as simple as that. And also, if the extension of each member is required using the relation, this one you are seeing also over here. Okay, just as we solve some places ago. Okay, so at the end of the day, this is just a summary of whatever we've spoken about. Okay, so we want to look at some examples. But even before then, I want to take some questions. Is anyone having any question to ask? Any question to ask before we proceed? Any question? Anyone having any question to ask? Any contribution? Okay, so that is very, very, very wonderful. Okay, exactly. So let's quickly start by solving some example. But for today, because this example, we already solved this example in class, I want us to now start solving the trial questions. Okay, so we are moving straight to the trial questions. Exactly. Exactly. So we are going straight to the trial question to start solving questions from the trial questions. And these are some questions that we are having from the trial question. At least if you're able to solve 2 of this, is good. Yes. So we want to start with what? Trial 1. Okay. We want to start with trial 1. That is question 5.1. Exactly. Question 5.1. Question 5.1. So our problem says that a composite bar consists of a circular rod of steel of 25 mm diameter, rigidly fixed into a copper tube of internal diameter 25 mm and external diameter 40 mm, as shown in the figure below. If the compound bar is subjected to a load of 120 kilonewton, find the stresses developed in two materials. Take elasticity of steel to be 2 times 10 exponent 5 Newton per millimeter squared, and elasticity of copper to be 1.2 times 10 Newton times 10 exponent 5 Newton per millimeter squared. Okay, so you can see this is the material over